Well, welcome back to our next review topic. Today we're going to cover derivatives of different types of exponential and logarithmic functions. Our first section is going to cover something called the derivative of a to the u, where a is a constant. Alright, so let's kind of review that definition here. If I have a to the u, and that u can be anything, its derivative is equal to a to the u, so you leave it alone. You take the derivative of u, and then you're going to take the ln of the base. So let's just make a few notes here. Notice this one, you are keeping the exact same. Here you're taking the derivative of whatever you called u, and then again the natural log of the base, not the exponent. Alright, so let's try our first example. Let's say we have the derivative of 6 to the 3x. Start with a nice easy one. Okay, so your first step, just like we read here, is going to be to keep it. So 6 to the 3x. And then you need to take the derivative of u. Well, notice in the rule, u is just your exponent. So on the bottom here, I'm just going to say u equals 3x. Therefore, the derivative of u is just equal to 3. So I'm going to say times 3, and then the ln of my base, which is 6. Now, we've talked about in class, since this is just review, that if you don't see that answer as the choice, the AP can get a little sneaky. They can just use those ln properties. So for example, this 3 in front, the ln property says if there's a number in front of your log, it can go up to the exponent. So I could have 6 to the 3x times the ln of, I'll just do it in steps here, 6 cubed, which is really 6 to the 3x, times the ln of 216. And again, I'm only doing this if I don't see my multiple choice answer. Example 2. Take the derivative of 3 to the raised to the 4x squared plus 2. Pause it, try it on your own, see if we get the same thing. So this is me keeping it, the derivative of my exponent, so I guess I didn't write that step out, but my u is just my exponent. My du is its derivative. So that's what goes in that second place. And then the ln of the base 3. Now notice, I'm not going to take this and raise it to the exponent because it's not just an entire constant. So I'm just going to leave it as is. Alright, example 3. The derivative of pi to the x tan x. Now, a lot of people get stumped on this one, but remember, pi is just a constant, so it is the same rule. Okay, and the other thing you should just catch is when you read that exponent, it says x times the tangent of x. So make sure you catch the word times and do product rule up there. So again, pause it, try it on your own. And hopefully you followed my work and have the same thing. Notice I did my u and my du right there. So we got x to the x tan, or pi to the x tan x, leave it alone. Derivative of the exponent, ln of the base. Alright, let's move on to our second topic. The second topic is just taking the derivative of e to the u itself. Okay, so let's say the derivative of e to the u is e to the u du. And now technically it's the ln of e. It's the exact same rule. Okay, but a lot of times we ignore that last part because the ln of e, well, that takes care of the zap rule and that turns into 1. So a lot of times we'll just say this. But in fact, if you want to throw that in there and cancel it out, by all means go ahead. It's just an extra step. Alright, but it is technically the same rule because e itself is also a constant. So let's say e to the 6x. Okay, so my u in this case would be 6x. My du would be 6. So my derivative would be e to the u, leave it alone. Just like we did in the other problem, times the derivative of my u, which is 6. And again, if I really wanted to say the ln of e, but it will cancel out every time. So it's the exact same rule we just did, but with that ln of e canceling out. Let me give you a few more to try. Number 2. Take the derivative of e to the sine x divided by x. So again, just watch yourself. When you see this, hopefully you're saying, I see quotient rule. So take your time with that derivative, pause it, and check back with me. I've got e to the u, I left it alone. Here's my u, here's its derivative, so I'm just multiplying by the derivative of that exponent. Alright, number 3. E to the negative 3x times the sine of 5x. So again, notice when I read that, I said this times this. Watch your product rule, pause it, try it on your own. And again, hopefully you follow my work and we get that same answer. Just watch that product rule, first derivative of the second, plus second derivative of the first. Alright, I've got one more of this type for you, and then we'll move on to our next type. Number 4, Let's just combine the two properties. Let's take the derivative of e to the 6x minus 6 to the ex. All right, so again, pause it, try it on your own, and we'll compare in a few moments. So check my work there. My e to the u is leave it alone, derivative of the exponent, minus leave it alone, derivative of the exponent, ln of the base. All right, our next little topic. Derivatives of natural logs. So here's our rule. To take the derivative of the ln of u, okay, and u can be anything, we say it's du over u. The derivative of what's inside there divided by what's inside there. Example 1. Again, we'll start nice and basic. The derivative of the ln of x cubed. All right, so all together, we're just picking our u is what's inside there. So u is x cubed. My du then is 3x squared. And the rule is du over u. So I would say 3x squared over x cubed, which of course reduces to 3 over x. Okay, so what we're saying to ourselves for ln's, du over u. Number 2, the ln of x to the 4th plus 8. Pause it, try it on your own, see if we get the same thing. So I've identified my u and my du, and again, just du over u. Nothing can clean up. Remember, if you can't cancel from every term, you're not going to cancel at all. Now, the ln properties, or derivatives here, can get a little more interesting, and let me give you the next example. Let's say we have the ln of 3x square root of 3 plus x. Now, a lot of people just want to dive into find your u and your du, and then do du over u. And in fact, sometimes in the ln properties, it makes it a little tougher to do that. And if you think back, there are 3 ln properties that you have. Okay? When you see multiplication, you can change it to addition. When you see division, you can change it to subtraction. And then you have that exponent that you can bring down in front. All right, so there's 3 ln properties. Now notice, none of those properties are about addition. So if you look back to this previous example, you could not split anything up because the addition is not a property. But now in this example, you see multiplication, and multiplication is a property. So you're almost crazy if you don't rewrite this. And that's one of the big catches in the ln's. If it's possible, if it's one of these 3, you can rewrite. So I'm going to say this is really the ln of 3x plus the ln of the square root of 3 plus x. Now you might be saying to yourself, you can rewrite this another way, and I'm going to do that as well. I'm going to say, again, like I see multiplication in here, so I'm going to say this is the ln of 3 plus the ln of x, plus, I actually see an exponent here. I can rewrite this as this chunk to the 1/2 power. So I can say this is 1/2 ln of 3 plus x. And again, I've done 0 calculus. All I've done is those 3 rules that you learn in Algebra 2 trig. And it's going to make this problem a lot easier if you rewrite it. Now you can easily go through and take the derivative of every term. Well, the ln of 3, remember that's just a constant. So its derivative should be 0. This is du over u. Okay, so my u is x, my du is 1. That gets me 1 over x. Plus I have a 1/2 in front. My u is 3 plus x. My derivative of that is 1. If I clean that up, I've got 1 over x plus, I'm going to distribute my 2 through, so I'm going to say 6 plus 2x. Now, they might actually want you to go further and get a common denominator if you don't see it as a multiple choice. So basically, I just say I need one of all these terms. So I need an x quantity and a 6 plus 2x quantity. This fraction gets multiplied by the 6 plus 2x, and this by the x. So I would say that's 6 plus 3x over that quantity. All right, let's just try one more ln example where we have to break it up and see if that helps. Let's say we have the ln of, say, x sine 6x plus 2. All right, so again, I could do my du over u, it's just going to be a little messy, or I could say it says x times this quantity, and times is a property. So I'm going to say it's really the ln of x plus the ln of the sine of 6x plus 2. Now notice I'm not breaking this chunk up. This is in the sine function, and that's not a property at all. All right, pause it, try it on your own, see if we get the same answer. So hopefully our answers match up there. Again, I'm going to go get my common denominator just in case they wanted that. So I would say I need an x and the quantity sine of 6x plus 2. This fraction gets this numerator gets multiplied by the x. This numerator gets multiplied by the sine of 6x plus 2. So I'm getting the sine of 6x plus 2 plus 6x cosine of 6x plus 2. All right, well, we've got one more little topic for the night. Stay with me, and here we go. All right, this section is titled Derivatives of Variable to a Variable. Now, we have several rules we have to follow in order to do this. The first thing you want to do is take the ln of both sides. Now, notice this is not any calculus work. This, again, is your Algebra 2. You're just taking the ln of both sides. Your second step then would be to take the derivative of both sides. And then, of course, your third step is to solve for dy, or whoever you're taking the derivative of. And then lastly, I just want to remind you that you normally substitute something back in. Okay, we normally substitute something back in. All right, so let's attack our first problem here. And again, we'll go nice and easy. Let's say y equals x to the 10x. Okay, and you know it's variable to a variable because take a look at it. The base is a variable, and the exponent contains a variable. So if we look at those steps, it's to take the ln of both sides. So you're literally slapping the word ln in front of both sides. Okay, now I'm doing this in steps. You could obviously do it in less than 2 steps, but I'm going to do it in 2 steps. When I do that, here's the ln property that says this exponent can come down in front. So I'm going to say this is the ln of y equals 10x. So I'm going to use that parenthesis there to represent my exponent, ln of x. And I suggest you do that. Put that exponent in parentheses. So that was technically step 1. We took the ln of both sides and we used our log properties. Step 2 now is to take the derivative. Okay, now notice my main variable is x. So when I take the derivative of this, I'm getting dy over y. Okay, it's like my du over u. So now I'm doing product rule because it says 10x times the ln of x. First times the derivative of the second plus the second times the derivative of the first. And lastly, my goal is to solve for dy dx, so I'm just multiplying both sides by y. I've got dy equals y times this whole quantity. These x's cancel, so that's 10 plus 10 ln of x. And lastly, we said you're probably going to substitute something back in. Well, in this case, we know what y is. Okay, y was given to us. That was the original question. Y equals x to the 10x times this quantity. Now, you'll notice that you might be able to pull out a GCF. You could obviously pull out a 10 there, so I'm going to go ahead and do so. I'm going to get my dy is actually, if I pull out the 10, that leaves me with a 1 plus the ln of x. And there's your variable to a variable rule. So let me just give you 1 or 2 more to try here, and we should be good to go. Let's say y equals x to the cos x. All right, pause it, you're on your own, and I'll get my work up in a few moments. Pause it, try it on your own. All right, well, here's my work. Notice I took the ln of both sides. Okay, now this exponent comes down in front. So I just kind of underline, that's not calculus, that's just Algebra 2. I took the derivative of both sides, dy over y, got my nice product rule here, multiplied both sides by y, so I've got this nice answer. And then lastly, just substituted that y value back in. So again, if you need any slowing down, pause it, rewind it, do what you need to do. We've got one last one for the variable to a variable. So example 3, let's say y equals the quantity x minus 4 raised to the 2 over x. Okay, so again, pause it, try it on your own, and we'll meet back. Alright, well hopefully you can follow my work. I used my ln property here in red, which brought the exponent down, and then I just rewrote this as 2x to the negative 1 for myself. In blue here I took the derivative, dy over y, I've got my nice product rule. And oops, I caught one little typo here. This should be negative 2 over x squared, which I'll have to fix there as well. And then I've got dy equals y times that quantity. And lastly, I can just substitute that y value back in. And that y value was x minus 4 to the 2 over x times this quantity. And again, they might ask for a common denominator, maybe not if it's this ugly looking. My guess is not over that x squared term. Well, there you have it. We tried to review, 4 different days all together here. Derivative of a to the u, e to the u, derivatives of variable to a variable, and ln. Have a great night.